this complete. Okay, so start last lecture. Anything has a beginning and has an end as well. So we reached now the last lecture on this very condensed and comprehensive course on Beyond the Standard Model. And I hope really it was useful to give you some idea about different scenarios for physics beyond the standard model. And today we will discuss extra dimension, something complementary to what we have discussed so far. And in extra dimensions, we will be as usual brief and highlight the concept and the motivation to consider extra dimension. Then we study all the theory started, the story of the extra dimension started with, which is a Kaluzа-Klein theory, 1920 or so. And then we will go to the new fashions in extra dimension. It's called large extra dimensions. This is was starting with 19, I think 90 something. 99. Kaluzа-Klein, sorry, a large extra dimension, in particular what's called ADD, Arkan-Hamidi democracy Valley model. Then after this, also after this scenario was 1 or 2 years, Randall and Sondrom consider another type of extra dimension. It's called warped extra dimension. We will also mention to this interesting scenario, in fact, because this is makes now extra dimension can be infinitely large. You don't need to worry about extra dimensions, and we will see how to do that. And later, if there is a time, we may consider some collider signature for large extra dimension aspect. So it's not just the mathematics, extra dimension. It can be also it can also have some implications on the collider and on our LHC, for example. Okay, so let me start with the motivation. Why we should go beyond the 4 dimensions? Well, why not? Remember when I defined the standard model, I said one of the definition that it is 4-dimensional field theory, quantum field theory. So going to more than 4 dimensions, we agreed that this means we are going beyond standard model in a way or another. General relativity, in fact, is based on 4 dimensions, but you can look at the general theory of relativity and you find it is valid and correct, and in fact, it can work for any dimension. So 4 dimension is just chosen because our intuitions that we live in 4 dimensions, but the general theory of relativity itself can be valid for any dimension. And in fact, the existence of new spatial dimensions beyond this 4 dimension have been under consideration for 80 years, yes, since the Kaluzа-Klein, as I said. And in fact, Kaluzа in particular, in the time of 1920, time of Einstein, he submitted a paper about general relativity or gravity in 5 dimensions. And he was trying to show that with 5-dimension gravity, in fact, and I will explain this, in fact, we unify gravity with electromagnetic fields. Einstein was one of the paper was sent to Einstein, and he kept with him for a while. He was astonished by the idea, didn't like it, but he was concerned about the extra dimension, where it is, and how it affected the gravity. And Kaluzа at this time was not proposing, I will show you, he was trying to propose, he was not proposing solution for the extra dimension, not compactification, for example, like Klein came and they make it compactification, but he tried to make some conditions to avoid complexity from the 5th dimension. And this was not so convincing to Einstein. And then Klein came and solved the problem. Nowadays, the extra dimension, okay. Nowadays, we generalize the idea, not only general relativity unified with electromagnetism in the 5th dimension, in 5 dimensions. But also, maybe you can go to a higher dimension and then you can unify other forces as well. And in fact, the string theory, based on 10 dimension or maybe 11 dimension in F theory, and this 10 dimension, the 6 extra dimension, give you the opportunity to have more gauge fields, more forces to play role in 4 dimension, similar to this 5 dimension Kaluza-Klein. So the gravity in 5 dimension is seen in the 4 dimension as a gravity plus electromagnetism. And we will see that 1 dimension more give you this gauge field. Then when you have more extra dimension, you have more chance to see in 4 dimension gravity plus electroweak or UCD or whatever. So in SO10, in string theory, for example, in 10 dimension, you can have really all forces in 4 dimension come from the higher dimension gravity in this X dimension. So the whole forces, the unified forces will be gravity essentially. But then, depends on the dimension you are live in, you will see gravity plus something else. And we will see this idea how to be implemented mathematically as well. Then in large X dimensions, people try to use X dimension to solve our standing problem, this hierarchy problem, in fact. And now it can be also good addition and needed for discussing some cosmological implication like inflation or let us see how things, this is the motivation and why we are interested in X dimension. Look at the general relativity in 5 dimensions, the Kaluza's work. So as I told you in 2090s or 2091, Kaluza claimed that, let us not claim, try to work out the general relativity in 5 dimensions. So as I told you, general relativity is essentially for any dimension. So the metric that we usually use, G mu nu dx nu for mu and nu 1 to 4. Now you can consider Gmn dxn. Here for Kaluza-Klein, for Kaluza, it will be m from 1 to 3 to 5 or 0, 1 to 4. And in general, this could be any dimension. Then this metric G mu nu that we decompose it, you know, this metric 5 dimension. So let me decompose it to 4 times 4, and then 4 times 1, or sorry, 1 times 4, and then 4 times 1, and then 1 times 1. So I like 5 dimension matrix, I just block it like this. So this is will be 4 by 4. This is will be vector 4 times 1, because not 5th, because I block the block 1 by 1, I take it separate. And then this is vector, and this is transfers of this vector, and this will be the singlet 1, 1. So 5 by 5 dimension, we decompose many things in SU5. So this is similar. You decompose it to 4 by 4. This is G mu nu, our 4 by 4. And this is will be vector 4 times 1. And this is transfer mu, and this is mu, which is the transpose. And this is a scalar. Okay, he wrote it in the, or not he, I don't know in 21 how he wrote this metric, but conventionally in the books now, you will find that it's much simpler to define this as a mu, and this is a scalar field phi, and G mu to take it in this expression. The idea for us is just to have a metric 5 dimension, and you decompose it, and then our gravity will be the first block, which is 4 by 4 G mu nu, and then we have a vector on the right-hand side of this block, which is a mu, and then the fifth 5 component G5 will be just representing the scalar field. In principle, also, since we have this is function of x in general relativity, now it should be function of x and y. Y is the extra dimension. However, because I told you Kaluza at this time has no idea to how to handle and to deal with the fifth dimension. So he assumed what is called now cylindrical conditions, means all the metric MGMN is independent of the Y or X4. So partial G by partial X4 is assumed to 0. Why this? Because he wanted to have extra dimension, but not explicitly depend on Y. He still wanted that even phi, which is a scalar field in the fifth component, is considered just function of X. So he wanted to make all the dynamics respect to our coordinate. This is of course not correct assumption, but this is the Lorentz, the cylindrical conditions that he considered to simplify things and try to make just one approximation per time. So it's enough to assume extra dimension and to add all these extra components, but don't confuse yourself with, because if everything depends also in Y, then there will be dynamics in extra dimension, and then there will be flow of all the metric G nu and nu in the fifth dimension. Then he cannot control it. So he wanted to really, I will show you now the new terminology we used to avoid this problem. We call it brain. And without any explanation, we assume everything related to us is stuck on this brain, and only gravity propagates on the bulk. So the guy in 2090 is very good for him to think about the problem and try to solve it with this condition. I don't want all my field to propagate and have a dynamics in the fifth dimension. There is a fifth dimension. There is consequence of extra dimension that I have extra field and extra phi, extra vector field and extra phi. It's enough. It's first order approximation to 1920. Later on, someone tell me how it will depend on what. So this is what the issue, and this was not convincing too much even Einstein, because there is extra dimension, it's not dependent how to deal with extra dimension and so on. Anyway, we continue with this assumption. And assume even the scalar field, which is now in the string theory, this scalar field is called, or in our extra dimension fields now, we call it radian. This scalar field is playing, yes.
But for example, from Einstein's work, as we understand, with unified space and time, he made them dependent, like they are correlated. So the idea of increasing the dimension must be correlating other things, right? Or
no, you just extend the spatial dimension x1, x2, x3 to x4, and the time remains time. Okay, and then Lorentz transformation will be 5-dimensional Lorentz. It's exactly the same like 4-dimensional. So nothing really changed in general relativity for that.
Yeah, I know, but I mean the condition that it's independent.
No, the condition here is just as you know, we have similar condition when we have a symmetric, when we solve the Einstein gravity, we start with symmetric metric, or in cosmology, we just assume it function of time. Okay, so the metric can depend on one component, one coordinate or all coordinates. It depends on the assumption you make on the metric. So in Friedman, Robertson, Walker, for example, the metric is just g of t, because we derive it at ds squared minus d equal minus dt squared plus scale factor a of t times dx3 squared, for example. That's it. So only metric is one. A of t, A of t, A of t. So the metric is function of t. It's not function of x, it's not function of. For spherical symmetry, we usually avoid coordinate dependence. So here he used this logic and said, okay, to avoid, you were talking about spherical symmetry, you want homogeneity, you want isotropy, so you make conditions on your metric. By the way, Friedman, Robertson, Walker metric, partial g by partial x3, for example, theta, or partial phi, or partial even r equals 0. Okay, it has a function only on t. So this is not very ad hoc assumption. But with this assumption, and this is also, he assumed to normalize it to 1. Okay, I don't want phi. Although this phi, as I told you later on, we discovered that this is give the radius of the x dimension. But anyway, in that time, this is the assumption. So take G44 or G55 to be phi squared equal 1. And now solve the Einstein equations, the Einstein field equation for third dimension, G and Mn equals 0. Just for space, sorry, free for vacuum, G Mn equals 0. You take this very simple exercise, hopefully, like general relativity, you take this, and you need to calculate from the metric, but you don't need to calculate really the metric in details, because anything related to G mu nu, you call it G tilde of standard of Einstein gravity. So G tilde mu nu is a part came from R mu nu tilde, which comes from R mu nu related to G mu nu. So you don't need to calculate straightforward calculation, but you need to be smarter to decompose R to R5 to R4 plus something. R mu nu, R5, R mu nu 4 plus something. Always you get something from the A field. Phi is 1, so only the A field remains. Then he found that although I start with 3 vacuum solutions, Gmn equals 0, in 4 dimension, when I make a reduction or when I decompose this, I got the 4 dimension Einstein tensor G tilde, sorry, G double dot mu, no, G tilde or G what is? Tilde for the 4 dimension. G mu nu tilde will be not 0 as I started with in the 5 dimension, but will have some energy momentum tensor. Source term. From where this source term came from the A mu, and the source term energy momentum tensor will be like the energy momentum tensor of the electromagnetism, F mu nu, F mu nu. So you see, you start with gravity only and the vacuum in 5 dimension. You see, when I say you see it in 4 dimension, this means this equation. This equation is telling me in 4 dimension I will have a gravity with a source, and this source comes from the electromagnetic field or from the vector field mu. And then I have another set of equations when I take M is 0 and N is 4 or 1 and 5, whatever. Okay, 0 and 4, because we work from 0 to 4. You will get some different equations than this, and it turns out to be the Maxwell's equation. Nabla mu F mu nu with a 0 source, no charge, because we do not assume any charges. So the source for gravity will be the vector field, and the vector field will be free source equation, and Maxwell's equation is a free source. So in principle, yes, this equation, which is 5-dimension gravity, is split into 2 equations. One is 4-dimension gravity with source from the electromagnetic field and Maxwell's equation.
So in this equation of G in the constant, Kalwza assumed that the right hand side, which equals is for the matter.
No, but vacuum, no matter.
Yes, for there is no matter.
Yes, there is no matter.
But there is no baryonic.
Nothing at all.
Even there is no electromagnetic.
Nothing.
So it's like an ideal case. It's like an ideal case.
Yes, but he wants just to show you, I start only from gravity. No matter. Vacuum is 0. No whatever matter. He doesn't know at that time baryons and non-baryon. No matter. It was called dust and radiation and all this stuff. So no matter. And from the gravity, pure gravity, I can extract electromagnetism as a source for general relativity and as a free equation for Maxwell. So don't you see that this is really a kind of unification here? General relativity in 5-dimension, gravity in higher dimension is equivalent to 2 forces in 4 dimension. You can improve things by looking to the Lagrange. Later we will do much better than this, but I'm telling you historically, this is what he did, and this was really, you know, pioneering work at that time, because nobody thought about gravity in 5 dimensions can be split in 4 dimensions to 2 forces.
The second equation made this assumption that it's sourceless.
No. He obtained from the derivation. And like this one, he obtained from the derivation, because when he tried to derive the 4x4 G mu nu, he found it's not 0, but there is some extra term. He sent it to the right-hand side and they call it T mu nu, and it goes like that. Okay. So yes, general gravity in 5 dimensions can appear as 2 forces in gravity and the electromagnetism in lower dimension, in 4 dimension. And as I told you, if you go to 6 dimension and go to 7, 10 dimension, you get more than Maxwell's. You get a billion only for 1 dimension more, because now you could have more than a mu A or whatever, and this will work like non-abelian. So this is the way to drive all our gauge fields with gravity from extra dimension in string theory. Now, because Einstein was unhappy with this 5th dimensions, how to deal with this, then Mr. Oscar Klein came and assumed something interesting happens in extra dimension, again without any justification, but he is trying to solve the problem. He said the extra dimension, this 5th dimension, is different from the other 4 dimensions. We have 4 dimension infinite. Dimension from -infinity to +infinity for the time and x and y and z. But for the 5th dimension, y or x4, he assumed that it is compactified. And this is the first time terminology or word compactified used in physics. Maybe it was used in mathematics before. What he means by compactified, he said, imagine that this is compactified, and simple example of the compactification on a circle. So this means that the field, or whatever you have, field x or metric or whatever, you have x as function of x4, with 2 by r, the radius of the circle, you will have a round and you get the same point again. This is a compactification, okay?
So this is like the z-axis.
Periodic or what, sorry?
This is like the z-axis, the x4.
X4 is the extra dimension. So instead of making like extra dimension, x4 from 0 to infinity, he said, no, it is curled around some circle. And in this case, if I'm at this point, it's called x4, I have to check that after 1 circle around the circle, one round around the circle, I get the same point again. This is compactified, you know, you turn it around some circle. This means x4 plus 2 by r, x4 plus 2 by r will give you the same result of x4. Okay, and in this case, the x4 will not be infinite extra dimension, but very compactified. And it depends on r. This will be having very small or very large extra dimension.
So we're considering the convention 0, 1, 2, 3, 4, right?
Yes. 4 is the last one, it's 5th. Yes. So this is the way he tried to convince Einstein that there is extra dimension. 5th extra dimension, x4, but we cannot see, and this doesn't disturb our life and our equations. Why? Because it is curved, it is compactified, and in fact compactified on very small r. And we will see now what r should, what values of r should be. So this is, you see, x in u is not compactified; it is along all directions. This will be compactified. And the idea now, it depends. Usually you tell you that it is compactified, but because you are very far, you cannot see, and you can see this is like just single point. Okay, so it's not seen if you are quite far. Or quite far means you are not groping with enough energy or whatever. But when you become close to this extra dimension, you can see now, you can open and you say, oh, it's not points, it is just like a circle. This is all usually the example. I can tell you that I have a sheet of papers, I curl it, and I stand very far away. Anyone will see it as a line. Okay, but when he is become closer and closer, he found this is like a circle. So the extra dimension that I wrap this or I curl it or it could be hidden for a very far distance, but for closer, this can be seen. And this is the idea. R is a small if you are very far or you don't have enough energy to work this extra dimension. And it could be a bit. Once we do this, you know, this always like Fourier expansions or something like that, then you will expand x mu and you will have, for example, the metric g mu x comma y, you will have g mu function of x only, but now with some index because you will have this what's called tower or states or whatever, because we sum from n goes to minus infinity. And this will be, no, but before the end, let me say g mu of x times e to I by b times, you know, some momentum dot y. And because you wanted that g should be single valued function, single valued function, then if I take y, instead of y, I wrote y plus 2 pi r, then the momentum times 2 pi r should give me exponential. P dot 2 pi r should give me 1, because this is exponential, essentially e to I p dot y. So I change y to y plus 2 pi r. This we should have a pen or something. But anyway, this is simple. This is usually quantization, we call or whatever, because this is now to be single valued, this exponential should be 1. So the exponential b dot 2 pi r equal 1 implies that b should be n integer times n over r, because r cancel with r and n2 pi exponential n2 pi is 1 always. So this is the point why we get here n over r. This is because I removed the fifth dimension momentum b5, which was multiplied times y, because now it should be quantized. It should be given in terms of n over r. So I wrote it like this. Okay? Yes.
But for example, if I took a slice of this, so this will correspond to a certain value of n, right?
No, no.
The summation.
No, wait, just wait. Slides here always will give you something similar. You will have some specific x and x4 still circle. Okay? Okay, but now this is really, this is not this is the metric, this is the function which depends on x and y of this form. So the a, not even the metric, a, b, whatever. Any function, if it, for that reason I said Fourier expansion, not just this one. If I have a of x comma y, I can write it as a of x times e to I b dot y. But why change it to y plus 2 pi r, and it should give me the same result. This is impose a condition on the b5 or by or whatever to be integer number over this radius r. So this is why I wrote it here like I n y dot r. And now we have some, because from the exponential, and from writing the momentum in terms of this n, I will have some n equal 1, n equal 2, and so on. So this is the same story for the metric, for the H field, for the scalar if it is there. And now really we have only the field in 4 dimension plus extra exponential effects. But we have a tower. We have values run from minus infinity to infinity, or you can see it like this. And the 4 dimension, the real 4 dimension, when we have no y dependence, when n equals 0. So n equals 0, this is called the 0 mode, and this is where represent us. Any n equal 1, n equal 2, n and so on, And in fact, we don't worry about minus infinity because there is a relation star n equal n a of minus n. So the complex conjugate is equivalent to minus n. So minus infinity equivalent to infinity complex conjugate. Minus 10, you can replace it by 10, but complex conjugate. So the essential from 0 to infinity. 0 is very good for us because this is the values of the metric with no dependence on y, and this is we call the 0 order, and this is what we are interested in. Okay, so Kaluzak-Klein describe according to this expansion infinite number of 4 dimensions. Okay, because I have A0 multiplied by this expansion, A1, A2, A3, and infinite number. Okay, and this is what is called the Kaluzak-Klein tower, KK tower. Okay, we go to the field equation for the metric, for example. As usual, we have a 5 dimensions, so we have the box, partial mu, and also partial y, act on the metric, which if it is depend on G of x, comma y. You will tell me, okay, comma y, you make it depend on y. Yes, the assumption was not depend on y, was Kaluza, but Klein, when he came and assumed compactification, now he returned, removed the condition of cylindrical conditions and allow for y dependence, and showed that y dependence is not a problem, but you need to compactify it as we discussed. Now, with this assumption and this compactification, your 5-dimensional equation, you have explicit dependence on y, exponential e to I n y over r. Then the derivative over y squared will act and give you n squared over r squared.
So does that mean that the compactification is equivalent to the condition that Kaluza?
No. Kaluza was killing the dependence at all. Klein can keep the dependence and make assumption about the x dimension to be in this framework.
Okay. So is there an advantage here and disadvantage there?
Of course, there's advantage in Kaluzak-Klein that you really make the 5th dimension active. What is the point to make a 5th dimension and then to forbid any dependence on it? It was very hard and harsh assumption. But as I told you, the guy was in trouble to keep it and then cannot control it. So he made this harsh assumption. Then the client came and said, okay, we have 5th dimension and it should be compactified, and I will see you the consequences now. Okay, and then we will see how the story will continue with the new fashions of work with exclamation and so on. So the consequences is, this is what I was telling you. The equations for the fields, metric or mu or phi, even he returned phi as a normal scalar field, not just taking one like in cylindrical condition. So for that reason, I'm considering the 3 variables, G, and A and phi, function of x and y. But we know all of them are function of x times exponential. And then the field equation, that the derivative respect to y squared, give me n squared over r squared. N squared over r squared, n squared over r squared. And this now field G mu, but with index r. So as we said, n field, n metric now, not just one metric. And n gauge field, and the n phi tower. So you have it 0, 1, 2, 3, and so on. You see now if n equal, first of all, this is like the Klein-Jordan equation or the field equation, wave equation, but with mass term. So all fields will be massive with n squared over r. We call it mn. Because it has n dependence. You remember hydrogen atom when we solved it and we got n and everything was related to n. Now everything is related to n. So we have mn equal n over r. And then people said, come on, this means the photon will be massive and the graviton will be massive or what? No, they will not, because we are interested in the 0 for our graviton and our photon is a zero mode. So the zero mode will have zero mass because n squared fortunately on the numerator. However, there is Kaluza-Klein excitation of the graft. There is Kaluza-Klein excitation for the photon, which means the n equal 1, n equal 2, and so on. And those will be massive. 1 over r, 4 over r squared, and so on. But those are Kaluza-Klein, which is tower, is higher dimensional, higher. It will be very heavy. We should assume it to be quite heavy to decoupled, but in principle they are existing.
But the excitation is like, for example, for the it's like giving it more momentum or something. The definition for the word excitation.
It is not excitation, because excitation, as you said, you give more energy and more excitement. But this is it's called the tower Kaluza-Klein. Maybe excitation in terms of higher n, but not really energy.
But it doesn't have any physical meaning. I mean, the higher.
No, as we have seen, in general in fifth dimension, we have more than one field, more than one metric and one gauge field. So we have some n dependence came from excitation in the sense that this momentum, the zero momentum, and then the first momentum, second momentum, because remember this is the momentum before. So higher momentum, in the sense of excitation is used there. Higher momentum, higher energy is the same, right?
Yeah.
So this is higher value of the momentum. So zero momentum means n equals 0. So this is three level or zero states or whatever. And therefore n equal 1 and so on. In principle, you could call it excitation.
Because in the other equation, the wave equation.
Also the same.
As you increase n, the mass term is increasing.
Yes, yes.
That's what put my attention.
I agree, but I think the whole issue came from this relation. This is the momentum, and the momentum now is integer, is defined as n over r, and 0n give me 0 momentum, 0 eigenstates, and 0 metric, the G0 that we are interested in. And unfortunately, G0 is massless. A0 is massless. And also phi 0, the scalar field, will be massless. So this will be our 4-dimensional metric gauge field and the scalar. Okay, maybe scalar, massless scalar is a problematic. We need to should be massive, but this is another issue in principle. And in addition to 0 states, we have higher states. You call it excitation, you call it Kaluza-Klein towers, you call it whatever, but we should know the source. The source comes from the compactification, and the fifth momentum is quantized, is n over r. Different values of n give me different values of states. Okay? Yes?
We can see this theory predicted large spectrum.
Infinite.
Yeah, infinitely large spectrum of mass for photons and gravity.
Infinite. But where they are, I will tell you. No, the lowest scale, 0 hour, high scale, that we cannot probe it at all.
Yes, I mean
we are low. We are low. Unfortunately, we are low. Nothing. Because nothing. Because it is the 1 over r, and we will see. We will identify like m blank. So 1 over 1 m blank, 2 m blank, 3 m blank, whatever m blank is m blank. And you are here very low energy, and the gap between, when you reach m blank, then you can ask between m1 m blank and 10 m blank and so on. But all of them are few times m blank.
So they are not detectable.
This is the whole point. And this was the strategy adopted since Kaluza-Klein 1920 until
string theory.
No, not string. String theory also consider the same things. To make the 1 over r is m blank. It's very, 1 over r, m blank means r, the length is blank length. it means the compactification scale length, the radius of the compactification 10 to minus 34 or something like that. Not detectable at all. And this was the standard procedure until 2000 or 1990 something, when large X-dimension fashion came. And I will tell you what they do to avoid this and to make some excitation at rather TV scale or so. But before going to this point, let me explain carefully that all these fields now should be separated like zero mode, phi 0, phi 0. And this is, for example, for the scalar, we'll give you Klein-Jordan equation as normal, partial mu phi 0, partial mu phi 0, no mass term. This is the zero mode. Plus higher modes or Kaluza Klein excitations, and those are with n different from 0, and those will have a mass term. So you see kinetic term, they are dynamic. They are not any auxiliary or whatever. They are dynamical fields with kinetic term similar to the 0, but the difference that they have mass term. And fortunately, the mass term is given in terms of n over r squared. So take r very, very small, you make the mass very, very large and of order Planck scale. Here is the towers I am telling you about. So each of those will have mass which is m0 if it is different from 0. For example, the photon m0 is 0, graviton m0 is 0. Phi could have a kind of different. Anyway, m0 is the original mass, and then you have corrections of order n squared over r squared from the compactification of the fifth dimension. And you see now this is a zero mode, and then you have n equal 1, n equal 2, n up to. And the difference between any two modes in the mass is of order 1 over r squared. So this is what's called the Kaluza Klein mass spectrum for a field compactified on a circle. Okay, remember this is on a circle, because if you compactify on something else, you will get something 1 over r squared also to have a very heavy mass, but not simple n squared over r squared. This is for phi or whatever. The gauge field also will do the same. You will have zero mode, which will be our Maxwell's equation. You start with the normal FMN 5 dimension, and if you compactify, you get F0 mu, and you get is A5 because here we take the mu A5 by itself. This is not the metric decomposition I'm giving you now. Imagine that you start with a gauge field in 5 dimensions. You will have A4 and A5. A4 will have the usual Maxwell's equation. A5 will work as scalar field because you decompose the vector to small vector and the scalar field. And again, the zero component or the zero mode of the scalar field A5 will be massless. Okay, and then we have a massive higher orders from n equal 1 to whatever, what's called Kaluza Klein excitation of Maxwell's field and mass term as well. So it becomes Broca fields, not Maxwell.
So the zero term are the physical terms and the other terms?
All of them are physical, but zero term means the term which is low energy, is the one we will probe it and we will deal with. But all of them are physical.
So the other things are physical, but we cannot detect.
Exactly. In another universe, maybe they will live in Planck scale. They will see this, and the A0 for them is far away, and they cannot see. So it depends where you are standing. So this is the situation after you compactify, and I give you here the first example, the scalar in this Lagrangian, how the scalar field will be decomposed and how the compactification will affect the higher modes with massive term. And then this is the tower of the scalar field. Now this is a vector field. We realize it that vector field compactified to vector field and the scalar field massless and higher components. And in higher, we don't need to higher terms. This Fm and this is the mass of the A mu n. Okay, now the graviton will have the same story. This is an equation of the graviton, for example. And we are saying, okay, general quantum transformation or gauge transformation, GMN, and blah, 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 just to show you that in the graviton, in fact, the metric you divided to G, F, and phi, and this is will be the final action. So you will end up with R, the Hilbert-Einstein action for 4 dimension, and then the 0 mode for F give you Maxwell's, and also 0 kinetic term for scalar field, assuming that you divide the metric to G mu G mu nu and A mu and phi. G mu nu give you capital R, A mu nu give you capital F, and the phi remains phi 0. Where the higher orders is the F term, N term condition. Yes.
So, for example, if we look at the Brans-Dicke theorem, it's basically removing the F mu part. I need this equation. Brans-Dicke theorem and minimal coupling.
General relativity.
General relativity.
Because
so we basically the symmetry, but we remove the F mu part and couple the reaches.
This is a different story. I know you have in Brans-Dicke's theory the scalar field coupled with gravity with non-minimal coupling, as you said. But here, really, the gravity is not R, is just R. Here, the coupling is phi is equal. And in fact, the phi, I told you the phi is playing role of some Higgs or some fields that will be minimized and will have a VEV. And you see now, this is in the string theory, especially we call it the dilaton. And this phi, when it takes a VEV, this is will give you the coefficient in front of F squared, which is the coupling. And the coupling, which here is the coupling, electromagnetic interaction coupling. The coupling usually will have 1 over G squared, F mu nu, whatever. And this is comes now dynamically from the vacuum expectation value of the scalar field phi. So even the coupling, you remember we have in the standard model 19 couplings, we have no explanation. A gauge, forget about gauge couplings, we have at least 3-4 gauge coupling. Now we try to explain the values of the gauge coupling by some potential and some scalar field, get a minima, and the VEV of this field will represent the coupling of this. So the story, if it is complete, will be completed, it will be wonderful.
So Professor, if we increase the value of the scalar field phi, this variable, the exponential, there will be no,
it will die, yes.
It will die, there will be no coupling.
No, but the minimization is not at infinity. Exactly. The minimization of the potential v of phi as some constant phi, which and we have to avoid running away potential. Okay,
yeah,
so
that's why we assume that decaying exponential.
Yes, yes. So this is the situation for the decomposition and the consequences when we have fifth dimension. Okay, and this is the standard and the old scenario valid until now even. However, as I told you, okay, before telling you, we have one more slide to discuss the matching process. What's the matching process? If I have a 5-dimension, let me start with the 5-dimension Hilbert-Einstein action. Okay, and also 5-dimension gauge field, GF gauge field. And this is in 5-dimension, it will be written like this. This is maybe very simple because it will be, it's not 5-dimension 4 plus n, but let me just call it 5-dimension now, n equal. So this will be d5x, okay? And 1 over g squared coupling, I was just telling you, fmn, because time the metric because
Yeah, they are connected because
it should be d4x. This square root g comes here because this is a measure of the integration.
We're considering curved space-time.
Yeah, this is a measure of the in the flat space-time, the square root of the metric is 1. So this is will be hence square root g4 plus x. So it is here because we curve it back out. So let me continue with this. This is simpler. Okay. Now, in the second slide. Okay. And before going to the second slide, let me also discuss Hilbert-Einstein action. So now Hilbert-Einstein action was a G Newton, right? In 4 dimensions. And G Newton, if you remember, it was M blank squared. It is G Newton. Yeah, it's dimension -2, so it is M blank squared. Now, if I have more than 4 dimension, M squared means 4/2. So when I have N plus 4, then it will be subtract 2. This is N plus 2 M star. So the dimension of the coupling constant will be not M blank that we know, but M star times power N plus 2. And again, the Riche scalar, but not for 4 dimension, but for 5th dimension or R plus N, times this integration measure, d4/5 square root of g5.
So in the M star N plus, it was N plus 4 minus the 2 of the M of the G Newton, right?
No. This will be like this is like G Newton star, for example. Okay, how we get the dimension of the G Newton star? How we know in 4 dimension G Newton is dimension mass squared. Okay, you calculate the dimension of this Lagrangian, subtract it. So the dimension there was just it should be what? Hilbert-Einstein action R and multiply by G. It was a square. It should be you need the action, not the Lagrangian should be. I think this was dimension mass square because the Lagrangian was dimension. The Lagrangian was -2 or what? Let us do d4x again. d4x is 1 square root of R. So the Lagrangian here, sorry? You are saying something, Murad?
No.
Okay, because I heard something from your side. Okay. So this is what the Lagrangian square root G.
Oh, sorry. I logged in and I think my mic is on. That's what you're hearing.
Okay. And I think square for this is the 4, and square root G times R in general relativity. Square root G, I think it is square the determinant G. This is dimensionless, so only R, and R is like higher derivative partial mu. How we define R? So dimension, it is known that the graph is non-renormalizable. So it has dimension, I guess, negative mass -6, negative masses. So multiply, we know, and the d4x it gives you 4. So you need 2 from the metric, from the coefficient. So
we also were trying to make it
not normalizable. You need the action to have a dimension 0.
Okay.
So the square root G times R there was giving you -6. This is giving you 4. Sorry?
The -4 dimension. The dimensions of -4 for the dx, right?
d4x -4 and this is give you only 2, dimension 2, so it remains -2. You have to multiply it by mass 2 at this. Here, I guess, will be more. This is what if the 5 dimension will give you dimension -5, and this is will be I don't know how much, and then you have m cubed. We can calculate it. This is remains, it seems, r square, mass square, and this is -5, so it's -3. You need to multiply it by m star 3. We call it m star to be different from m blank, our m blank. So this is just to balance the dimensions and to have the action dimension less. Otherwise, you cannot define the exponential is and you make the unitary. Okay, so I take this action now, Hilbert-Einstein action, and I will make the decomposition. So okay, this is m star remains m star, and the d for n plus 4x, I divided to d4x, and the 5th dimensions will be like d omega radius Rn. This is all, if it is just 5th dimension, it will be just a dy, whatever. But because he considers general n dimension, so he take all the measure as d omega n times radius Rn. Okay. Don't confuse Rn with this R Ricci scale. This is just the radius of n spatial dimension. So like a sphere, we have Rn, d omega, the angle, solid angles, this give you the measure dnx, essentially. So he separated dnx in this form and the d4x, and he separate also square root g to power 4 times r4. Where g5 he I think divided. He divided to whatever other components, but I don't care. I want just to match gravity, so I take only r4, okay, from r5. And then this is the new action in 5th dimension, written in terms of 4-dimension metric plus the measure of the 5th dimension. I should compare it with the one we know this. M blank, our M blank square, d4x square root g4 r4. Okay, so you can see that this is essentially this one. M blank should be this issue. And then we divide, we realize it that our M blank in 4 dimension is given by M blank in higher dimension, which we call it M star, to some power 2 plus n, time this volume integration d omega Rn, as I told you, the radius time the angles, blah, 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 give you what we call the volume of x dimension. Okay, so the relation now between M blank at gut scale, M blank at high scale, at large scale, large x dimension, and the M blank in 4 dimension will related to the volume of the compactification. And from here, people said, okay, this is the point. Since this relation here, the volume could be written in terms of R to power n, then R itself will be M blank to some power over M star to some power. Okay, so it depends now, either this one or this, depends on now how small and how large R. If R is quite small, as we claim, then M blank should be quite large. M blank, because now, M blank to power 2 over n. Also, this is taken of order M blank. So this cancels with this, and it will be 1 over M blank that I told you. So you take it very small, and you take it of order 1 M blank. This is F, M star is equal M blank. But in principle, this is not necessary, okay? And the people started to think that I want the M blank to avoid the hierarchy problem, to be close to the electroweak. And maybe the gravity large scale will be the M star. And then I will play M blank much smaller than M star. And in this case, R will not be suppressed and small like 1 over M blank, but it could be larger. But in any case, in this scenario that I told you here, that we could have R of order 1 over M blank, and the length will be of order 10 to the minus 32, and this is the one we said this is the standard, this is the default scenario we are considering. And this is comes from the matching condition, matching the gauge field, matching the gauge field. If you match the gauge field in that relation, 1 equal R n M n star, but this is another step. Let me just focus on this issue, that the M blank in 4 dimension is related to M blank in higher dimension, with dimension a little bit higher. So it is, if it's 4 dimension and 5, so M blank square will be M star cubed times the V of R. You increase the volume, then you have this is could be small times large, and then M blank could be 10 to 19. You reduce the volume, this is could be M blank with this is very large. So it depends on the volume. M blank could be how large it is. From the matching of the electromagnetism, is very easy because just the volume and nothing else. So you get 1 equal R and the M star. Okay. So once you know M star from here or from here, you can have a relation about the length, the radius of the conductivity. R equal 1 over M blank, combining these two relations from this and this. Okay. Let me tell you that when I combine the relation, I assume there is a matching for gauge field and matching condition for the generativity. This means gauge field is propagated. We have a gauge field on 5 dimension and the gauge field in 4 dimension, and I'm trying to match. And I said to have this match, then the 1 should be Rn to M star, right? Because there is no M blank in 4 dimension gauge field, but there is M star comes from the volume, and the volume you use this relation. Okay. But when we go now and assume brane like this, in the brane we assume that all standard model particles lives only in 4 dimension, localize it in 4 dimension, and they have no chance to propagate in the particle. So you don't need to worry about matching of the electromagnetic field or gauge field, right? Because it is stuck on 4 dimension. There is no propagation in the bulk. This is another brane in the other side, and this is the extra dimension. So we started to like this this room. This is 2 dimension. This is 2 dimension. This is the bulk. We call it the 3rd dimension or 4th, and the whole things. This is space. So this is now hypersurface. We call it brane, where the particle physics standard model particles lives on this brane. And there is no really mechanism to guarantee that you localize your particle on the brane. This is deep string theory, where string theory attached to brane and so on. Still, also this is again contains assumptions more than proof, but this is the way we started to think of extra dimension. That to make ourselves safe, let us delocalize it in hypersurface 4 dimension. And the other hypersurface, this is we call the dark sector, dark brane. You remember supersymmetry breaking? I told you it should be broken in some dark sector. This could be broken here in the dark brane. And then the gravity is the only mediation between these 2 branes. Okay, so this is the cartoon and the setup we consider so far for X dimension. Yes.
So what I understand is that we can only detect the other sheets from gravity, like gravity waves.
If gravity moved to you any information from the other, yes.
How could we know that it's from the other side?
Huh?
How could we know that it's from the other side if we don't know what it is?
Because like Susie breaking, you don't have it here, and then you have it from here, and then it appears to you suppressed by M Planck. So suppression by M Planck means this is gravitational interaction.
But we don't know anything about this dark sector.
No, we started to allow for Susie breaking in this dark sector. You started to assume some field there, get back. The F term and the D term is not vanishing in this sector, and then the effect of the F term and the D term is not directly connected with us, but it's connected via gravity. Therefore, it comes to us proportional to 1 over M Planck. Okay. What I want to say that now I don't need to worry about the matching condition of the gauge field. I have only one condition to match, is a gravity, Hilbert-Einstein action. And then we return back to the original expression that we obtained for the radius, R equal M Planck to power 2 over N over M star. This is the relation, and this is the setup that Mr. Arkan Hamid and Mordas came and realized that, oh, we can have large R. How you can get large R? You want M Planck with 4-dimension M Planck to be large, 10 to 19 GeV. That's fine. Don't take M star M Planck, because if you take M star M Planck, as we said, this will cancel with this, and it will remain 1 over M Planck. But if you take it something else, TV scale, and then M star, the 5-dimension Planck is a fundamental scale of order TV, and you have something in 4-dimension, we call it M Planck 10 to 19 GeV, then the radius R will be something much larger. Okay, and then they realized that I can do this if I take M star TV, that R will be like 10 to power 30 over N. N is a number of extra dimensions, 1 or 2, 5 dimension or 6 dimension, in centimeters times TV scale over M electron V times some power. 10 to minus 17 comes from M Planck, which is 10 to 19. So they just substituted numerically. Okay, and they substitute M star with the TV scale, and they try to normalize it over GV or 1 over TV, whatever these values. But this is no relation. Now, if in this scenario, if you take N equal 1 dimension, which we was happy to consider 5 dimension, with N equal 1, this will be 10 to 30 minus 17. So something like 10 to 13 centimeter. And this factor of the extra dimension will be 10 to 13 or so centimeter, which is how many? 10 to 10 or 10 to 11 meter. So the extra dimension becomes like very large. So of course this cannot be, and this ruled out. And therefore they take it at least 2 dimension, extra dimension. In this setup of ADD, it should be at least 2 dimension. To reduce this is to 10 to 15 minus 17. So this will be 10 to minus 2 centimeter, and some factor from here. They claim, okay, we are in the millimeter, and then they realize that they should push it a little bit to micro. So millimeter, this means quite large. You were talking about 10 to minus 32 or 34 meter, or in blank units, blank length. You go many order of magnitude to 10 to minus 2 or 100 micrometer, millimeter of magnitude. You know why they refuse this large centimeter extra dimension? Because you modify Newton's law. Newton's law, it will not be 1 over r squared, but it will be modified, and they destroy your gravity at even low scales. So the deviation from Newton's law would be accommodated by the experimental limit of gravity. So up to millimeter or less than millimeter, the gravity experimental limits on gravity is acceptable. The modification in the Newton's law will be within the observations. So this is the reason why they stuck with 2 dimensions, and they have the extra dimension millimeter or micrometer. However, this is something different from what we usually use. Which one is correct, which one is wrong? Millimeter and assume grains where particles stuck, and all this kind of assumption. 2 extra dimension, not 1. Why not? Why not 1? Why not? Why only 2? Why not 3? Not 4? Because once you increase by 3, 4, you started to reduce the extra dimension radius more and more. Therefore, in the string theory, when we have 10 dimension, it's natural to have the radius back to blank scale, blank length. Okay. So again, this is just a function of the number of the radius.
But say you didn't take this radius, even this one that's 100 micrometers, and n equals.
What do you mean?
Like for example, based on what they decided, okay, let's assume that
they take n equal to with this 500 micrometers, and then they study some consequences.
And they detected it.
They claim there's some theoretical arguments and some trial to predict something, some other astrophysics constraints and remains, and then people realize that maybe n equal to is not enough, and we have to go to lower values, larger. Okay, then maybe it's a dimension, string or whatever, and the story stopped at. I cannot see any more work in this. But also the Randall syndrome that we will discuss was a reason to stop this chapter quickly and to go to the other chapter of work with extra dimension, because it is much more elegant from my point of view. Here is a consequence, as you said, prediction or something like that, because we have n equal to, and we have, remember, n here is a dimension, a number of the extra dimension. N of the Kaluza-Klein excitation is the modes. So we have many n, we have many r, so don't confuse yourself. We have a Kaluza-Klein excitation because we have extra dimension, in principle compactified with some radius r and a larger r and so on. So larger r means not very heavy, not very heavy. Remember, when the r was small, the mass was blank of the Kaluza-Klein, so no chance to discover. But now is it 1 over micro means the mass, which is the inverse of the radius, is of order TT scale. This is the LHC energy. So people study now the Kaluza-Klein excitations, how we can drop it and make E plus and minus collision, and a lot of work in G minus 2, blah, blah, blah. But all of this was good exercise, putting some limits, but no observation for any signals. And all this process, E plus, E minus, and all this, it's propagated by Z and many, many, many other particles. So it's very difficult to distinguish that this is Kaluza-Klein, not something else. However, there's possibility too, because this is a tensor field. So in principle you can, but it's really difficult. However, people tried, and even tried long-lived the Kaluza-Klein graviton, make some analysis how they affect the astrophysics and blah blah blah. So this is some consequences related to particle physics. Now we go to Randall syndrome and the idea that we could have extra dimensions, right? But the metric will not be in the standard way that we have used before. So in fact, the idea of branes, which came from string, by the way, string theory, the first place suggested branes, and Wojcicki worked a lot on this. And then those people of X dimension, they just take it and assume it like that. And brain is not something simple. It has, several issues should be satisfied and fulfilled. And string theory was doing that, but they take it from out of its context and they just assume our full dimension in this brain and other things. Then Randall and Sondrum said, okay, we have 5 dimensions and we have the metric. In fact, we could have it like this. G mu nu of x, the coefficient dx and dx nu, but we could have also function of y. Like G, the metric G mu nu x and comma y, and you make factorization, f of y. However, this dy's, dya, dya, if one dimension more, this will have a metric of y only. Okay, this is the way, and again, they assume compactification and blah, blah, blah. And they found that one of the interesting scenarios when you allow for this f of y, remember f of y here or g of y here can be absorbed in the definition of y. You make y prime, which is related to f times y, and you write it again, you take it this is for y. So the only important factor is f of y in front of d, g, mu nu x, and dx and mu dx. And now when you solve any g, any f of y in this, you can write it as exponential function. And you solve, you get this exponential as e to minus some constant mod of y, the x dimension. So this is like, as you said, is annihilating, is reducing, is vanishing at you. If this brane at y equals 0, then it fill our metric. And once you go little bit far, you will have kind of reducing and suppressing factor. This is what we call warped factor. So the metric, the whole metric is warped, is reducing. You see that you started from here, dx nu times g nu factor 1. So this is the brane. And once you go a little bit far, the metric will be reduced by factor, I don't know, 10 to minus whatever. And this is why we have a reduction until we reach that other place.
Is this like a conformal transformation?
No, it's not conformal because it doesn't come from any transformations. In fact, it's coming from the solution of you include this, and as I told you, you normalize this to 1, and then you try to solve like Einstein equation where you solve to get the metric.
Yeah.
And now the metric, there is one part which depends on the y, will give you separate equation, you solve, you get exponential solution.
Yeah, but what confused me is that here we modify the metric, we shrink it, but it has always the same.
Right, I understand. Conformal will do something similar, but I don't want to say it is transformation because this is really a solution and the outcome of the Einstein equations in 5 dimensions. So this is as once you allow f of y to be remember in Kalwza Klein, we allow g mu nu x comma y, but we did not separate y as a function of y, but we just compactify y, and then we write g mu nu of x y as a g mu nu of x times the exponential n over r. So this is a compactification. They said, no, we don't need to compactify. For that reason, they call it alternative to the compactification. You don't need to compactify because you keep y as a whole extra dimension, and the solution will give you this warped factor. They call it warped, not conform, warped factor. And now you feel that everything will die out once you go from our brain. Okay, because this factor. Apart from only gravity goes out, they still assume that our particle physics stuck on this brain. Even gravity now is not propagating everywhere. So it's not propagating everywhere. So the modification of Newton's law and the gravity's law will be limited because its impact orbit factor. This will reduce immediately the effect of gravity outside. Even if you have very large extra dimension, will not spoil your Newton's law. So this is the whole point. Now you don't worry. You don't need to worry about the dimension, the what's called the length or of the extra dimensions, large or small. It is there, large or small. We don't care. In fact, in the first model, they just put the second plane here, and they said this is orbit factor, and everything will be satisfied nicely without worrying about the extra dimensions length. And then they realized that, okay, even I don't need the second plane, I can take it away. Very well. And then they call it, in the second paper, infinite extra dimension. So in this scenario, extra dimension will be infinite like the other 4 dimensions, which is nice because why the 5th dimension, curlets, compactified, everywhere. However, due to this orbit factor, due to like exactly in matter fields and gravitational interactions and electromagnetic forces and so on, stuck on the brain, gravity will not be stuck on the brain, but it will propagate with orbit factor, which make it almost localize it to the brain, and things will be peaceful and without any dramatic.
But in that case, Professor, the other brain will not feel gravity, right?
Our gravity, yes.
There will be no connection between us and the other brain.
Yeah, especially if you push it very, very far away.
Yeah, it's not there. So it's like assumptions and theoretical work.
Okay, this assumption again, when we do the matching conditions with this work factors and all this stuff, we will get very similar but interesting result for M blank. Remember M blank and M star, and there was a ratio related to R. Here is no R, in fact. And here was just M blank over the kappa, the factor kappa in this work factor, times 1 minus the work factor. This will die quickly, and this will be M cubed over K, and in fact, K is of order M, and M square will be of order M blank square, and therefore we have 1 M blank. We don't have several M. So they were trying to solve the hierarchy problem like what ADD did, and find the small lower M star that, but this will not work here. Okay, so M blank. And then Randall Solder discovered that they cannot solve the hierarchy problem with orbit factor. However, it turns out not hierarchy problem, forget about hierarchy problem, this is particle physics problem, but this is interesting scenario for gravity, for extra dimension. You don't need to worry about compactification, towers, blah, 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 but just orbit factor to allow the gravity to propagate in the bulk in very particular and very big bulk.
So, Professor, it was like, in this case, it was like a trick, the other brain, because we assumed another brain, and then we took it away to the point that we want.
Because it was not useful.
Yeah, exactly.
In fact, in the other brain, they tried to say this is the TV scale, and we will leave in the TV scale and the blank scale with MP, M blank will be the other. And then we discovered that we cannot live in the TV because we have to be in the brain where Y equals 0, the tension, positive tension. So there's some details here, but then they realized that the hierarchy is not solved in this scenario. And then they gave up hierarchy problem and they consider just solution. And this is what they try to do. If we call it blank brain, and this is the hidden, and this is hierarchy. Sorry, this is the invisible brain, our TV brain. And the idea now, it was really to consider us here, not there, And in fact, they found that M equal M blank, so M blank is not changed in any of those two. But the vacuum expectation value for the Higgs will be here of order M blank, and there will be affected by the work factor, and it becomes V effective. So the hierarchy between Higgs vacuum expectation value, why it is 100 GeV, not M blank. It is true that you can obtain it by allowing for kappa Y of order 11, and this is taken V, which is M blank, then this is will reduce it to 100 GeV. And this is could be explanation. However, to get this value here, you are in the wrong brane. You are in the wrong brane, where gravity is suppressed, where the tension is negative, tension which is related to the cosmological constant. So the cosmological constant is negative. This means you live in anti-de Sitter space, and we know that we live in de Sitter space, not anti-de Sitter space. So it turns out that no, we cannot be in the TV scale brane, although we gain explanation for 100 GeV vacuum expectation value of the Higgs and solve the hierarchy. And then they decided to remove this, and we leave here, we call it this is blank brane and the visible brane and the hierarchy problem here, and everything is here. But at least we have a consistent gravity and consistent field and the consistent cosmology is de Sitter or vacuum. So in this model, after they take the brane far away, becomes, as I told you, infinite extra dimension. In fact, infinite extra dimensions, and everything was working fine, but mass hierarchy problem was not solved, and they forgot it. This is some possible again signatures if we have kind of excitations from the gravity, of course, because only gravity has a Kaluza-Klein excitation, and as usual, some trial for some signatures E plus E minus to E plus E minus, and there's some peaks, hopefully some discovery, but so far. I am not sure about Kaluza-Klein excitation at LHC, but this is, if Kaluza-Klein is not very heavy scale, in principle, why not? But I think the consistency and the gravity construction, and also the issue of standard model on branes and the hierarchy problem issue, and all this is more important and more serious than just to convince me that there is Kaluza-Klein prediction at LHC, unless they discover the prediction. But as I told you, this channel they are talking about several particles, essentially all particles could contribute. So we need really to work harder to get. This is what called the Randall syndrome 2, when they take out the brane, second brane, and as I told you, just one brane and infinite extra dimensions. Okay, and still, although infinite extra dimension, gravity will be localized, and this is the potential of gravity. So the potential of gravity from this, when they consider the solution of gravity, they got what's called volcano potential, where you know around this the gravity potential of the gravity it's vanish quickly, and this is known as a volcano potential. And I think there was some excitement about this type of potential for gravity, but I don't know if it gives any specific or any concrete prediction for this type of gravity, because the gravity is not stuck for, it's not propagated forever for extra dimension. It's kind of a specific type of interactions, but maybe the work factor is quick by quickly this curve, so maybe the effect is not yet seen. But this is idea considered so far in market. Even orbit geometry and the branes are in the string theory, in fact, and they may be more rigorously, but not easily studied. But all these ideas still, you know, people trying to get something final from out of this. Okay, that's all. We reach the final as well. So there is chat here. Yes, I can attend. Okay, we are almost done with this lecture. So please let me know. Here they asked Murad or who is us? Only Murad. So do you have any questions, Murad?
No, not
Okay.
really. Yeah.
It's far from your work. Good. So this is the last lecture.
Yeah, I mean,
we took a tour, start from standard model to Higgs doublet, SU5, SUSY, extra dimension. Sorry if I was too much, too heavy for you, but hopefully it will help you.
Actually, you know, Shaban, in addition, I just need to make a comment that I think these extra dimensions can be connected with the composite Higgs models by anti-de-Sitter conformal field theory. This was the lecture given by last week by Raman Sundaram, the one that you mentioned. Yeah, so
yeah, maybe I am not familiar with this, but yeah, we try to get use of any useful information from that exercise I mentioned. But I believe it should be first from gravity and from understanding the universe. Particle physics will be second. So you know, their motivations was a hierarchy problem, and it turns out that they cannot really explain it.
yes, exactly.
So if they try now to, but who said we need composite Higgs? We have fundamental Higgs. So why ADS-CFT extra dimension to motivate composite Higgs? We have fundamental Higgs. I don't know if they still doubt that the Higgs is fundamental.
I think, well, actually, composite Higgs models also, I mean, the motivation behind it is the hierarchy problem, just like supersymmetry.
Hierarchy problem?
Yeah, the motivation behind composite Higgs model.
Why? If it is composite, they will not have a radiative correction? Why?
Well, I didn't read in detail, to be honest.
Yeah, I also cannot see if it is composite or fundamental. Unless it's composite, then there is some symmetry protected, which is not exist in the fundamental singlet scalar, maybe. But you know, to solve a problem with invoking, you know, ADS-CFT and extra dimensions and the compositeness, too much. So make it simple, and fundamental scalar Higgs is discovered, and I think it will be proven that it is real fundamental. I have no doubt it's fundamental scalar. Anyway, the development of the particle physics come always from, you know, accepting idea and refusing this, proposing strange things and try to prove it. This is life in physics in general. But okay, if Sandram gave a talk about the ADS-CFT composite Higgs, we can look at it. Where is he now? Where is he now?
Sorry?
Where is he?
You mean Raman Sundaram?
Yes, because after that paper with Randall, we never read Sandram.
Oh yeah, I think he left, I think, last week.
Sorry?
To US.
So he's a professor in, I know, in Stanford or somewhere in
Maryland, I think.
Maryland? Okay,
Yeah.
okay. Somewhere. But I haven't seen a lot of work as before. Okay. Also, Lisa, after this paper, we wrote a book and make a lot of interviews and becomes public figures more than scientists, physicists, to do calculations with these things. But anyway, their work for extra dimension, work with extra dimension was appreciated.
I see.
Sorry? Well, I am open-minded to see, but I think Susie still have good chance. It's, you know, all beyond the standard model, only Susie is restricted, and you know the energy of LHC is pushing everything high. But not only Susie, we didn't discover anything else to say Susie is in that situation. It's BSM in general, I would say. And among the BSM, I don't know, for me, I can still see Susie, but maybe not, as I was telling them yesterday, not the minimal Susie with the three parameters. So maybe non-minimal Susie could be, or I don't know, we are open. We are waiting for any guidance from our experimental colleagues. But if you compare Susie at low energy or extra dimension at low energy, I think Susie maybe still have a chance. SU5 or GUTS or whatever with all the even theoretical complication. Susie has only one complication issue. I told them Susie breakneck. This is the only things missing theoretically. Anyway, we keep it open for all. We didn't focus on Susie only. You know, we could take the whole week for super sampling or the whole week for ground unification, but we decided to give you just a hint about everything, because as we were saying now, all beyond the standard model under questions so far. So it's very useful to be aware about what's going on in general and to be prepared for some surprise. Maybe obtained at LHC run 3. Yes.
So, Professor, almost all these models are the current proposed
yes.
models so far.
Yes. If there's something else, I will bring it to your dish. But this is mostly the most relevant. Yes. Okay, I enjoyed. I hope you also enjoyed, and we will have next week another hard work week with a lot of talks, short but long, short but many. So hopefully you will also enjoy the conference. Okay, Murad, bye bye.
Thank you. Bye bye, Shaban. Thank you for nice lectures. Thank you.